Hello viewers, from the bottom of my heart, I am both excited and concerned about the topic of brain-computer interface and artificial intelligence. The reason for my excitement stems from the rapid advancement of technology. It seems we are on the cusp of entering an era where mere thoughts can translate into actions, eliminating the need for physical movement. Such a development holds the promise of benefiting individuals of all ages, with gadgets responding to our desires with just a mental command. It's a paradigm shift centered around the power of the human brain, where the installation of a chip could unlock boundless possibilities for our future. In this context, we should feel optimistic, proud, and joyful about the potential this technology holds to enhance our lives. The video accompanying this message elucidates how this technology can seamlessly execute tasks, thereby offering myriad benefits that could significantly improve our quality of life. However, juxtaposed with this excitement is a sense of apprehension. Viewing this advancement through the lens of an average individual, one may naturally contemplate the potential implications on our daily lives. It's essential to consider how such technology might impact our autonomy, privacy, and even societal dynamics. Therefore, I have made a deliberate choice to address this aspect towards the conclusion of the video. I urge you to watch until the end to gain a comprehensive understanding of both the promises and potential pitfalls of this transformative technology. Please like, share, and subscribe. Thank you very much. Let's start the topic. Introduction to BCI. Imagine being able to control your computer, play a game, or communicate with someone all without moving a muscle. That's the promise of brain-computer interface (BCI) technology. At its core, BCI is like a bridge between your brain and a device, such as a computer or a robotic arm. It allows you to send commands or communicate just by thinking. Here is how it works. Your brain generates electrical signals whenever you think, move, or feel something. BCIs pick up these signals, decode them, and translate them into commands that a device can understand. It's like your thoughts are being turned into actions by magic. For example, imagine a person who has lost the ability to move their limbs due to a spinal cord injury. With a BCI, they could still control a computer or a wheelchair using their thoughts alone. This can vastly improve their quality of life and independence. BCI technology has also found its way into the world of gaming. Some companies are developing BCIs that allow players to control characters in video games using their minds. It's like something straight out of science fiction. Types of BCIs. Invasive, non-invasive, and partially invasive approaches. BCIs come in various forms, each with its own way to interfacing with the brain. The three main types are invasive, non-invasive, and partially invasive BCIs. Invasive BCIs. Invasive BCIs involve the placement of electrodes directly into the brain tissue. These electrodes record neural activity with high precision, offering detailed information about brain signals. While invasive BCIs provide excellent signal quality, they require surgical implementation, which comes with risks and limitations. Example: neural implants used in research labs to study brain function or in medical settings to help individuals with paralysis regain control over their limbs. These implants allow for precise control but require surgery and carry risks associated with invasive procedures. Non-invasive BCIs. Non-invasive BCIs do not require surgical implantation and instead rely on external sensors to detect brain activity. Common non-invasive methods include EEG, which measures electrical activity on the scalp, and FNIRS, functional near-infrared spectroscopy, which measures changes in blood oxygen levels in the brain. Non-invasive BCIs are generally safer and more accessible than invasive methods but may offer lower signal quality and spatial resolution. Example: EEG headsets used in research, gaming, or consumer applications. These headsets detect brain activity through sensors placed on the scalp, allowing users to control devices or interact with virtual environments using their thoughts, while less invasive EEG-based BCIs may have limitations in terms of signal accuracy and noise interference. Partially invasive BCIs. Partially invasive BCIs involve placing electrodes on the surface of the brain or within the skull but without penetrating brain tissue. These approaches aim to balance the advantages of invasive and non-invasive methods, offering higher signal quality than non-invasive BCIs while avoiding the risks associated with the implanting electrodes into the brain tissue. Example: electrode arrays placed on the surface of the brain in epilepsy monitoring or brain-computer interfacing. These arrays provide better signal quality than scalp-based methods while minimizing the invasiveness and risks associated with penetrating the brain tissue. Each type of BCI has its own advantages and limitations, and the choice of approach depends on factors such as the specific application user requirements and safety considerations. By offering a range of options, BCI technology strives to provide accessible and effective solutions for interfacing with the brain and improving human-computer interaction. How BCI works? BCI technology works by decoding the electrical signals generated by the brain and translating them into commands that can control external devices. Brain signal acquisition. First, sensors or electrodes are used to detect brain signals. These sensors can be placed directly on the scalp in non-invasive methods or implanted inside the brain tissue in invasive methods. The signal recorded include electrical potential generated by neuron firing in the brain. Signal processing. The raw brain signals captured by the sensors are then processed to extract relevant information. This involves filtering out noise, amplifying the signals, and analyzing their patterns. Signal processing algorithms play a crucial role in extracting meaningful information from the complex neural activity recorded by the sensors. Feature extraction. In this step, specific features or characteristics of the brain signals are identified. These features could include frequency patterns, amplitude variations, or special distributions of neural activity. Feature extraction helps to simplify the data and identify relevant patterns that can be used to interpret the user's intentions. Classification. Once the relevant features are extracted, machine learning algorithms are often employed to classify or interpret the brain signals. These algorithms learn to associate patterns in the brain signals with specific commands or actions. For example, a particular pattern of brain activity might be associated with the intention to move a cursor on a screen or to select an option from a menu. Command generation. Based on the classification results, commands are generated to control external devices or applications. These commands could include moving a cursor, selecting an option, typing text, or controlling a robotic arm. The commands are sent to the target device, where they are executed to perform the desired action. Example: consider a non-invasive BCI system using EEG sensors to control a computer cursor. The EEG sensors detect electrical activity on the scalp, which is then processed to identify patterns associated with different types of cursor movements: up, down, left, right. Machine learning algorithms analyze these patterns and classify the user's intentions. Based on the classification results, commands are generated to move the cursor accordingly on the computer screen, allowing the user to navigate the interact with the interface using their thoughts alone. Overall, BCI technology enables direct communication between the brain and external devices, offering new possibilities for individuals with disabilities, gaming enthusiasts, and researchers studying the brain. Through the translation of brain signals into actionable commands, BCIs empower users to interact with the world in novel and meaningful ways. BCI components: electrodes. Electrodes are sensors that detect electrical activity generated by the brain. They come in different forms depending on the type of BCI system. In non-invasive BCIs, electrodes may be placed on the scalp to measure electrical potentials, while invasive BCIs may use microelectrode arrays implanted directly into the brain tissue to capture neural signals with high precision. Example: EEG electrodes are commonly used in non-invasive BCIs. These electrodes are placed on the scalp and connected to the BCI system to record electrical activity from the brain's surface. Amplifiers. Amplifiers are devices that increase the strength of the electrical signals detected by the electrodes. They ensure that the weak electrical signals generated by the brain are amplified to a level that can be accurately measured and processed by the BCI system. Amplifiers play a crucial role in improving the signal-to-noise ratio and enhancing the quality of the recorded brain signals. Example: EEG amplifiers amplify the weak electrical signals detected by the scalp electrodes before transmitting them to the signal processing unit of the BCI system. Signal processing algorithms. Signal processing algorithms analyze and interpret the electrical signals recorded by the electrodes. These algorithms extract relevant features from the raw brain signals, filter out noise, and classify patterns associated with different mental states or intentions. Signal processing algorithms play a key role in translating brain activity into actionable commands for controlling external devices. Example: machine learning algorithms such as support vector machines or convolutional neural networks are commonly used in BCI systems to classify patterns in brain signals and decode the user's intentions. These algorithms learn to associate specific patterns in the brain signals with different commands or actions. Output devices. Output devices are the interfaces through which the user interacts with the external world based on the commands generated by the BCI system. These devices receive commands from the BCI system and translate them into actions or feedback that the user can perceive. Example: output devices in BCI systems can include computer screens, robotic arms, virtual reality headsets, or speech synthesizers. For instance, if a user intends to move a cursor on a computer screen using a BCI, the output device would translate the BCI commands into cursor movements on the screen, allowing the user to interact with software applications. By integrating these components, BCI systems enable direct communication between the brain and external devices, opening up new possibilities for assistive technology, gaming, research, and healthcare applications. Such components plays a critical role in capturing, processing, and translating brain signals into meaningful actions, empowering users to interact with the world in innovative and impactful ways. Applications of BCI, healthcare, assistive technology. BCIs can empower individuals with severe disabilities such as spinal cord injuries or locked in syndrome to communicate and interact with their environment. For example, individuals who are unable to move their limbs can use BCIs to control wheelchairs, robotic prosthetics, or communication devices using their brain signal. Neurorehabilitation. BCIs are used in rehabilitation programs to facilitate motor recovery in patients with stroke, traumatic brain injury, or spinal cord injury. By providing real-time feedback on brain activity, BCIs can help patients relearn movement patterns and improve motor function. Medical diagnosis and monitoring. BCIs have the potential to assist in the diagnosis and monitoring of neurological disorders such as epilepsy, Alzheimer's disease, and Parkinson's disease. For example, EEG-based BCIs can detect abnormal brain activity patterns indicative of seizure or cognitive decline. Gaming. Gaming BCIs are increasingly being integrated into gaming applications to provide immersive and interactive experiences. Mind-controlled games. BCIs allow players to control game characters, vehicles, or virtual environments using their brain signals. For example, players can move objects, navigate mazes, or cast spells in games using their thoughts alone. Enhanced immersion. BCIs can enhance immersion in virtual reality VR gaming by enabling natural and intuitive interaction with virtual environments. Players can experience virtual worlds more deeply through direct control of trained in-game avatars, actions, and movements. Communication. BCIs offer novel communication channels for individuals with communication disabilities or disorders. Augmentative and Alternative Communication AAC. BCIs enable individuals with conditions such as amyotrophic lateral sclerosis ALS or cerebral palsy to communicate by selecting letters, words, or phrases on a computer screen using their brain signals. Brain-to-brain communication. BCIs have the potential to facilitate direct communication between individuals' brains without the need for verbal or physical interaction. This technology could revolutionize communication for people with several disabilities or those who are non-verbal. Neurofeedback therapy. BCIs are used in neurofeedback therapy to train individuals to regulate their brain activity and improve cognitive function or emotional regulation. Attention training. BCIs can provide real-time feedback on brain activity related to attention, helping individuals learn to sustain focus and concentration. Anxiety and stress management. BCIs can help individuals learn to modulate their brain activity patterns associated with stress or anxiety, leading to improved emotional regulation and relaxation. Overall, BCI technology has diverse applications across healthcare, gaming, communication, and therapy, offering new opportunities for empowerment, rehabilitation, and human-computer interaction. As the field continues to advance, BCI applications are expected to expand, further contributing to improvements in quality of life, accessibility, and well-being for individuals around the world. Restoring mobility. BCI technology holds tremendous promise in restoring mobility for individuals with severe disabilities such as spinal cord injuries or paralysis. By bypassing damaged neural pathways, BCIs enable direct communication between the brain and external devices, allowing users to control prosthetic limbs, wheelchairs, or exoskeletons using their thoughts alone. Example: consider a person who has lost the ability to move their limbs due to a spinal cord injury. With a BCI controlled exoskeleton, they can regain the ability to walk by simply imagining the movements they want to perform. The BCI interprets their brain signals and translates them into commands that drive the exoskeleton's motors, enabling the user to take steps and move independently. Communication for individuals with disabilities. BCIs provide alternative communication channels for individuals with communication disabilities or disorders, such as ALS or logged in syndrome. By detecting and interpreting brain signals associated with language or intention, BCIs allow users to spell out messages, select words or phrases, and engage in real-time communication with others. Example: imagine a person with ALS who has lost the ability to speak and move their limbs. With a BCI-controlled communication device, they can compose messages by selecting letters or words on a screen using their brain signals. The BCI translates their intentions into commands that generate text or speech output, enabling them to communicate with caregivers, family, and friends. Medical diagnostics. BCIs have the potential to assist in the diagnosis and monitoring of neurological disorders or cognitive impairments. By analyzing patterns in brain activity, BCIs can detect abnormalities indicative of conditions such as epilepsy, Alzheimer's disease, or traumatic brain injury. Additionally, BCIs can provide real-time feedback during neuroimaging procedures, enhancing the accuracy of medical diagnostics. Example: in epilepsy monitoring, BCIs analyze EEG signals to detect abnormal brain activity patterns associated with seizures. By continuously monitoring brain activity, BCIs can alert patients or healthcare providers to impending seizures, enabling timely intervention and management of the condition. Overall, BCI technology is revolutionizing healthcare by offering innovative solutions for restoring mobility, communication, and diagnostics for individuals with disabilities and neurological disorders. Through direct communication between the brain and external devices, BCIs empower users to overcome physical limitations and lead more independent and fulfilling lives. Mind-controlled gameplay. BCIs enable players to control in-game actions and interactions using their thoughts alone. This mind-controlled gameplay adds a new dimension to gaming experiences, allowing players to immerse themselves in virtual worlds and interact with them in unprecedented ways. Example: in a racing game, players can steer their virtual car, accelerate, and brake by simply imagining these actions. The BCI interprets their brain signals and translates them into commands that control the car's movements in the game. This creates a seamless and immersive experience where players feel directly connected to the virtual environment. Enhanced immersion in virtual reality gaming. BCIs enhance immersion in VR gaming by providing natural and intuitive interaction methods. Players can navigate virtual environments, manipulate objects, and engage in gameplay using their thoughts, eliminating the need for traditional input devices like controllers or keyboards. Example: in a VR adventure game, players can explore fantastical worlds and interact with objects using hand gestures controlled by a BCI. By detecting and interpreting their brain signals, the BCI translates their intentions into in-game actions, allowing for seamless and intuitive gameplay without the constraints of physical controllers. Adaptive gameplay and personalization. BCIs enable adaptive gameplay experiences tailored to individual players' cognitive states, preferences, and abilities. Games can dynamically adjust difficult levels, pacing, and challenges based on real time analysis of players' brain activity, creating personalized and engaging experiences. Example: in a puzzle game, the difficulty of puzzles can adapt based on the player's level of focus or cognitive workload detected by the BCI. If the player shows signs of frustration or cognitive fatigue, the game can dynamically adjust puzzle complexity or provide hints to maintain engagement and enjoyment. Exploration of new game concepts and genres. BCIs open up possibilities for exploring new game concepts and genres that leverage the unique capabilities of brain controlled interactions. Game developers are experimenting with innovative gameplay mechanics, narratives, and storytelling techniques that harness the potential of BCI technology to create compelling and memorable gaming experiences. Example: imagine a narrative driven adventure game where players' decisions and emotions influence the unfolding storyline. The BCI monitors players' emotional responses and cognitive states, dynamically shaping the narrative and character interactions based on their real time feedback. This creates a deeply immersive and emotionally resonant gaming experience that adapts to each player's individual journey. Overall, BCI technology is revolutionizing gaming by offering immersive experiences, novel interaction methods, and personalized gameplay tailored to individual players' cognitive states and preferences. As the technology continues to evolve, we can expect to see even more innovative and captivating gaming experiences that push the boundaries of imagination and creativity. BCI in communication, alternative communication channels for individuals with logged in syndrome or severe communication disorders who are unable to speak or move. Traditional methods of communication may be limited or non existent. BCIs provide alternative communication channels by allowing users to convey their thoughts and intentions directly through brain signals. Example: consider a person with logged in syndrome, a condition characterized by complete paralysis of voluntary muscles, including those used for speech and movement. With a BCI controlled communication device, they can compose messages, select words, or express emotions by simply imagining the corresponding actions. The BCI translates their brain signals into commands that generate text or speech output, enabling them to communicate with caregivers, family, and friends. Real-time communication. BCIs enable real-time communication by providing instantaneous feedback on users' brain activity and intentions. This allows for natural and fluid interaction where thoughts are translated into spoken or written language in near real time. Example: a person using a BCI controlled communication device can engage in conversations with others by formulating sentences and responses in their mind. The BCI interprets their brain signals and converts them into text or speech output, which is then conveyed to the conversation partner. This seamless exchange of the thoughts facilitates spontaneous communication and fosters social interaction and connection. Customizable interfaces. BCIs offer customizable interfaces that can be tailored to individual users' needs, preferences, and abilities. Communication devices equipped with BCIs can be adapted to accommodate different communication modalities, languages, vocabularies, and communication speeds. Example: communication devices with BCI capabilities allow users to personalize their interfaces by selecting preferred input methods, that is, letter selection, word prediction, output modalities, that is, text, speech, and communication settings, that is, speed, vocabulary size. This customization ensures that communication aids are optimized for each user's unique communication profile, enhancing usability and effectiveness. Enhanced independence and empowerment. BCIs promote independence and empowerment by giving user greater control over their communication abilities and interactions with the world by bypassing physical limitations and enabling direct communication through brain signals. BCIs restore agency and autonomy to individuals who may otherwise be dependent on others for communication support. Example: with a BCI controlled communication device, individuals with logged in syndrome can initiate and participate in conversations, express their needs and preferences, and engage in social activities independently. This newfound ability to communicate empowers users to assert their identities, make choices, and actively participate in their communities, fostering a sense of self-determination and inclusion. Overall, BCI technology revolutionizes communication for individuals with logged-in syndrome or communication disorders by providing thought-based communication aids that enable real-time interaction, customization, and empowerment. By bridging the gap between the mind and external communication devices, BCIs offer hope and opportunities for improved quality of life, social connection, and self-expression. BCI and neurofeedback therapy, real-time feedback on brain activity. BCI-based neurofeedback therapy involves providing individuals with real-time feedback on their brain activity, typically through visual or auditory cues. This feedback allows users to observe and monitor their brain functions as they engage in cognitive tasks or exercises. Example: in a neurofeedback session, individuals may be presented with visualizations of their brain activity, such as EEG, waveforms, or functional brain maps in real time. By observing changes in their brain activity patterns, users can learn to modulate their brain function and achieve desired cognitive states such as increased focus, relaxation, or cognitive control. Cognitive enhancement. BCIs are used to train and enhance cognitive abilities such as attention, memory, and executive function. By providing feedback on brain activity related to specific cognitive tasks, BCIs help individuals improve their cognitive performance and overcome challenges related to attention deficits, learning disorders, or cognitive decline. Example: in a neurofeedback program targeting attention, individuals with ADHD, attention deficit hyperactivity disorder, may engage in tasks that require sustained focus or concentration while receiving real-time feedback on their brain activity. As they learn to regulate their attentional processes, they may experience improvements in attention span, impulse control, and task performance. Neurorehabilitation. BCIs play a crucial role in neurorehabilitation by facilitating recovery from neurological conditions or injuries, such as stroke, traumatic brain injury, or neurodegenerative disease. Neurofeedback therapy using BCIs can promote neural plasticity, facilitate motor relearning, and enhance functional recovery in affected individuals. Example: in stroke rehabilitation, individuals with motor impairments may undergo neurofeedback therapy using BCIs to promote motor recovery by visualizing and modulating brain activity associated with movement execution. Individuals can retrain neural circuits and improve motor function in affected limbs. This process may involve tasks such as motor imagery, mental rehearsal of movements, or motor execution with BCI feedback. Personalized training programs. BCIs enable personalized training programs tailored to individuals' cognitive profiles, goals, and rehabilitation needs. By monitoring and analyzing users' brain activity in real time, BCIs adapt training protocols to optimize effectiveness and address specific cognitive challenges or deficits. Example: neurofeedback therapy programs using BCIs can be customized based on individuals' cognitive strengths and weaknesses, as well as their rehabilitation goals, training parameters, feedback modalities, and task difficulty levels can be adjusted dynamically to maximize engagement, motivation, and therapeutic benefits for each user. Overall, BCI based neurofeedback therapy offers promising avenues for cognitive enhancement and neurorehabilitation, leveraging the power of real time brain feedback to promote adaptive changes in brain function and behavior. As the field continues to advance, BCI driven approaches hold potential to transform rehabilitation practices and improve outcomes for individuals with neurological conditions or cognitive impairments. Future implications for the average person: enhanced accessibility and inclusivity. BCI technology has the potential to enhance accessibility and inclusivity for individuals with disabilities, allowing them to participate more fully in daily activities, work environments, and recreational pursuits. By providing alternative communication channels, assistive technologies, and mobility aids controlled by brain signals, BCIs empower individuals with physical or communication impairments to engage with the world on their own terms. Hands-free interaction with technology. BCIs enable hands-free interaction with technology, reducing reliance on traditional input devices such as keyboards, mice, or touchscreens. This can enhance productivity, efficiency, and convenience in various tasks, from composing emails and navigating software applications to controlling smart home devices and interacting with virtual environments. Personalized healthcare and wellness. BCIs offer personalized healthcare and wellness solutions that cater to individual needs, preferences, and health goals. From neurofeedback therapy for cognitive enhancements to biofeedback for stress management and relaxation, BCIs empower individuals to make an active role in monitoring and optimizing their health and well-being through real-time feedback on brain and physiological signals. Augmented human capabilities. BCI technology has the potential to augment human capabilities and performance in various domains, including cognitive tasks, creative endeavors, and physical activities. By leveraging brain-computer interfacing, individuals can enhance their cognitive skills, creative output, and physical abilities through targeted training, neurofeedback, and brain stimulation techniques. New forms of entertainment and engagement. BCIs open up new possibilities for entertainment and engagement, offering immersive gaming experiences, interactive art installations, and novel forms of storytelling that leverage brain-controlled interactions, from mind-controlled video games and virtual reality experiences to brainwave-powered music composition and interactive exhibits. BCIs enrich layer activities and stimulate creativity and imagination. Ethical and societal implications. As BCI technology becomes more pervasive in daily life, it raises ethical, legal, and societal questions regarding privacy, consent, autonomy, and equity. Ensuring responsible development, deployment, and regulation of BCIs is essential to address potential risks and safeguard individuals' rights, dignity, and well-being in a rapidly evolving technological landscape. Overall, the future implications of BCI technology for the average person are vast and multifaceted, offering opportunities for empowerment, enrichment, and transformation across various aspects of life, work, and leisure. By embracing the potential of BCIs while addressing ethical and societal considerations, we can harness the full benefits of this groundbreaking technology to create a more inclusive, accessible, and human centered future for all. Universal Design Principles. BCI technology should be designed following universal design principles to ensure usability and accessibility for people with diverse abilities and needs. This includes considerations such as intuitive interfaces, customizable settings, clear instructions, and compatibility with assistive technologies. User-centered design approach. Adopting a user-centered design approach is essential for understanding and addressing the unique needs, preferences, and challenges of potential users, involving individuals with disabilities, caregivers, and diverse user groups in the design and development process helps identify barriers and opportunities for improving accessibility and usability. Accessible input and output modalities. BCI systems should support a wide range of input and output modalities to accommodate different communication styles, sensory references, and motor abilities. This may include alternative input methods, that is, eye gaze, facial expressions, voice commands, and output modalities, that is, text, speech, tactile feedback, tailored to individual users' capabilities and preferences. Adaptive and customizable interfaces. BCI interfaces should be adaptive and customizable to accommodate users' evolving needs, skills, and preferences over time, providing options for adjusting interface layouts, feedback modalities, and interaction parameters allows users to tailor the BCI system to their specific requirements and comfort levels. Training and support resources. Offering comprehensive training and support resources is essential for ensuring that users can effectively learn to use BCI technology and overcome any challenges that may encounter. This may include instructional materials, tutorials, training sessions, and ongoing technical support services tailored to users' learning styles and abilities. Affordability and accessibility of hardware and software. BCI hardware and software should be affordable and accessible to ensure equitable access for individuals from diverse socio-economic backgrounds. This may involve developing low-cost or open source solutions, leveraging existing technologies and infrastructure, and collaborating with stakeholders to reduce barriers to adoption and deployment. Awareness and education. Raising awareness and educating the public about BCI technology and its potential benefits for individuals with disabilities is essential for fostering acceptance, understanding, and support. This includes promoting positive representations of BCI users and showcasing real-world applications that demonstrate the transformative impact to BCI technology on people's lives. By prioritizing accessibility and inclusivity in the design, development, and deployment of BCI technology, we can ensure that everyone, regardless of their abilities or circumstances, has the opportunity to benefit from its potential to enhance communication, mobility, and quality of life. Privacy protection. BCI system records sensitive neural data that could reveal intimate details about individuals' thoughts, emotions, and cognitive states. Protecting the privacy of BCI users requires robust data encryption, anonymization techniques, and secure storage practices to prevent unauthorized access or disclosure of personal information. Informed consent. Obtaining informed consent from BCI user is essential to ensure that individuals understand the risks, benefits, and implications of participating in BCI research or using BCI technology. Informed consent should include transparent explanations of data collection, usage, storage, and sharing practices, as well as options for withdrawing consent and exercising control over their data. Data ownership and control. BCI users should have ownership and control over their neural data, including the right to access, modify, and delete their data as desired. Establishing clear policies and procedures for data ownership, consent management, and data sharing is crucial for empowering users to make informed decisions about their personal information and safeguarding their privacy rights. Data security and encryption. Implementing robust data security measures such as encryption, authentication, and access controls is essential for protecting BCI data from unauthorized access, interception, or tampering. BCI systems should adhere to industry best practices and standards for data security to mitigate the risk of data breaches or cyber attacks. Mitigating bias and discrimination. BCI technology has the potential to perpetuate or exacerbate biases and inequalities if not carefully designed and implemented. Ensuring fairness, transparency, and accountability in algorithm development, data processing, and decision making is essential for mitigating bias and discrimination in BCI systems and promoting equitable access and outcomes for all users. Regulatory oversight and compliance. Establishing regulatory frameworks and guidelines for BCI research, development, and deployment is essential for ensuring ethical conduct and compliance with legal and ethical standards. Regulatory agencies and professional organizations play a crucial role in monitoring and enforcing ethical guidelines, addressing ethical concerns, and promoting responsible innovation in the field of BCI technology. By addressing these ethical considerations proactively and collaboratively, researchers, developers, policymakers, and stakeholders can foster trust, accountability, and a responsible use of BCI technology while maximizing its potential benefits for individuals and society. Challenges. BCI systems rely on accurately detecting and interpreting neural signals, which can be challenging due to the inherent complexity and variability of brain activity. Factors such as noise, artifacts, and signal drift can degrade signal accuracy, leading to errors in command, classification, or interpretation. Strategies. Employ advanced signal processing techniques such as filtering, artifact removal, and feature extraction to enhance signal quality and accuracy. Incorporate machine learning algorithms that can adaptively learn and adapt to individual users' neural patterns over time, improving classification performance and robustness. Reliability. Challenge. BCI systems need to be reliable and consistent in their performance to be practical and effective for users. Variability in signal quality, user engagement, and environmental conditions can affect the reliability of BCI systems, leading to unpredictable or inconsistent outcomes. Strategies. Conduct rigorous testing and validation of BCI systems under various conditions and scenarios to assess their reliability and performance robustness. Implement adaptive algorithms and feedback mechanisms that can dynamically adjust to changes in signal quality, user state, or task demands, maintaining system reliability and usability in real-world settings. Compatibility with different users. Challenge. BCI systems must be compatible with a diverse range of users, including individuals with varying levels of cognitive abilities, motor skills, and neurological conditions. Designing BCI interfaces and algorithms that accommodate users' individual differences and preferences is essential for ensuring usability and effectiveness. Strategies: adopt a user-centered design approach that involves end users in the design and development process, incorporating their feedback and preferences into the BCI system's design. Provide customizable interfaces and adaptive features that allow users to personalize their BCI experience based on their unique needs, abilities, and preferences. Addressing these challenges requires interdisciplinary collaboration among researchers, engineers, clinicians, and end users to develop innovative solutions that enhance signal accuracy, reliability, and usability of BCI technology. By overcoming these challenges, BCI system can fulfill their potential to improve communication, mobility, and quality of life for individuals with disabilities and neurological conditions. Pros of BCI. BCI technology enables individuals with severe communication disabilities such as logged in syndrome or ALS to communicate independently using their thoughts alone. By bypassing traditional input methods like speech or physical gestures, BCIs provide a direct channel for individuals to express their thoughts, needs, and emotions, enhancing their ability to interact with others and participate in social activities. Increased accessibility. BCIs improve accessibility for individuals with physical disabilities by providing alternative control interfaces for computers, smartphones, assistive devices, and mobility aids. This enables individuals with motor impairments to access and interact with technology, navigate digital interfaces, and perform daily tasks more independently, thereby promoting inclusion, autonomy, and equal opportunities for participation in society. Potential for medical breakthroughs. BCI technology holds immense promise for advancing medical research and treatment approaches for neurological disorders, brain injuries, and cognitive impairments. BSIs facilitate non-invasive monitoring of brain activity, enabling researchers to study brain function, neural plasticity, and disease mechanisms in unprecedented detail. Additionally, BCI-based interventions such as neurofeedback therapy and brain stimulation techniques offer novel approaches for cognitive rehabilitation, pain management, and neurological recovery. Neuroscientific insights. BCIs provide valuable insights into brain function and neural mechanisms underlying human cognition, behavior, and consciousness. By analyzing patterns in brain activity recorded by BCIs, researchers can investigate fundamental questions about perception, memory, decision making, and learning processes, advancing our understanding of the brain and its role in shaping human experience and behavior. Assistive technology innovation. BCI technology drives innovation in assistive technologies, robotics, and wearable devices designed to enhance human capabilities and quality of life. By integrating BCIs with prosthetic limbs, exoskeleton, and smart home system, researchers develop assistive solutions that restore mobility, independence, and functional abilities for individuals with disabilities, facilitating greater participation and integration into society. Overall, the pros of BCI technology extend beyond individual benefits to encompass broader societal implications, including advancements in the healthcare, accessibility, and human-computer interaction. By harnessing the potential of BCI technology responsibly and ethically, we can leverage its transformative power to improve lives and shape a more inclusive and equitable future for all. Cons of BCI. Technical limitations. Signal quality and reliability. BCI systems may struggle with signal noise, artifacts, and variabilities affecting the accuracy and reliability of neural signal detection and interpretation, complexity and calibration. BCI systems often require complex setup procedures, calibration sessions, and user training to achieve optimal performance, limiting their usability and accessibility for some users. Limited spatial resolution. Non-invasive BCIs such as EEG-based systems have limited spatial resolution compared to invasive methods, which may constrain their ability to precisely localize brain activity and decode complex cognitive processes. Invasive procedures. Surgical risks. Invasive BCI procedures such as implanting electrode arrays into the brain tissue carry inherent risks of surgical complications, infections, and tissue damage, which may pose significant safety concerns for users. Long-term stability. Invasive BCIs may face challenges related to long-term stability and biocompatibility, including electrode degradation, tissue inflammation, and immune responses, which can affect device performance and longevity. Ethical concerns. Privacy and consent. BCI technology raises privacy concerns related to the collection, storage, and sharing of sensitive neural data, prompting questions about consent, data ownership, and potential misuse or unauthorized access to BCI data. Autonomy and agency. BCI systems raise ethical questions about autonomy and agency, particularly regarding individuals' ability to control and consent to brain-based interventions, neuroenhancement techniques, or invasive procedures that may impact their cognitive or emotional states. Equity and access. BCI technology may exacerbate existing disparities in access to healthcare and assistive technologies, as invasive procedures and advanced BCI systems may be prohibitively expensive, inaccessible, or unavailable to marginalized populations, further widening the digital divide. Social and psychological implications. Stigmatization and discrimination. BCI users may face social stigma, discrimination, or privacy concerns associated with their use of brain-based technologies, potentially leading to social isolation, identity challenges, or negative perceptions. Psychological impact. BCI interventions and neurofeedback therapy may have psychological implications, such as altering individuals' perceptions of self agency and identity, raising ethical questions about the potential risks and unintended consequences of manipulating brain function and cognition. Addressing these cons requires careful consideration of ethical, technical, and societal factors, as well as ongoing research, regulation, and dialogue to ensure responsible development and deployment of BCI technology. By addressing these challenges proactively, we can maximize the benefits of BCI technology while minimizing potential risks and ethical concerns, fostering a more inclusive, equitable, and ethically grounded approach to brain-computer interaction. Neuroethics. Informed consent. Individuals' autonomy and right to self-determination should be respected in all interventions involving brain interfacing or cognitive alteration. Informed consent processes should ensure that individuals understand the risks, benefits, and implications of the interventions, including potential changes to cognitive function, behavior, and identity. Privacy and confidentiality. Protecting the privacy and confidentiality of neural data is essential to preserve individuals' autonomy, dignity, and rights. Measures should be in place to safeguard against unauthorized access, disclosure, or misuse of sensitive brain-related information, including neural activity patterns, personal thoughts, and mental states. Enhancements versus treatment. Distinguishing between therapeutic interventions aimed at treating medical conditions and cognitive enhancement, interventions aimed at improving cognitive function in healthy individuals is crucial. Ethical considerations differ between these contexts, including issues related to medical necessity, safety, efficacy, and equity. Ensuring equitable access to brain interfacing technologies and cognitive enhancement interventions is essential to address disparities in healthcare, education, and societal participation. Efforts should be made to minimize barriers to access, including financial, social, and cultural factors, and prioritize the needs of marginalized and underserved populations. Identity and authenticity. Altering cognitive functions through brain interfacing or enhancement interventions may raise questions about individuals' sense of identity, authenticity, and agency. Ethical considerations include respecting individuals' self perceptions, preserving their core values and beliefs, and minimizing unintended changes to their personal identity or sense of self. Risk and safety. Assessing and mitigating risks associated with brain interfacing and cognitive alteration interventions is crucial to protect individuals from harm. This includes evaluating the safety, efficacy, and long-term effects of interventions, as well as monitoring for adverse events, side effects, and unintended consequences. Neurodiversity and neurodivergence. Embracing neurodiversity and recognizing the value of diverse cognitive experiences and perspectives is essential in ethical deliberations about brain interfacing and cognitive alteration. Respecting the rights and preferences of neurodivergent individuals, including those with autism, ADHD, or other neurological variations, requires sensitivity to their unique needs and preferences. Regulatory oversight and governance. Establishing regulatory frameworks, guidelines, and ethical standards for brain interfacing technologies and cognitive enhancement interventions is essential to ensure responsible research, development, and deployment practices. Regulatory oversight should address safety, efficacy, informed consent, privacy protection, and equity considerations while fostering innovation and scientific progress. By addressing these ethical considerations thoughtfully and collaboratively, researchers, clinicians, policymakers, and stakeholders can navigate the complex ethical landscape of brain interfacing and cognitive alteration interventions responsibly and ethically, promoting human flourishing, autonomy, and well-being. Neuroplasticity and BCI. BCIs can deliver targeted neural stimulation to specific brain regions or neural circuits, modulating neural activity patterns and promoting synaptic plasticity. By providing precise and controlled patterns of electrical stimulation, BCIs can induce long-lasting changes in synaptic strength, connectivity, and neural network dynamics, facilitating neural recognition and functional recovery following injury or neurological impairment. Neurofeedback training. BCIs enable real-time feedback on brain activity, allowing individuals to observe and modulate their own neural activity patterns consciously. Through neurofeedback training, individuals can learn to regulate their brain function, enhance cognitive control, and optimize neural circuits associated with specific cognitive functions or behaviors. This process fosters adaptive changes in brain connectivity and activity, leading to improvements in cognitive performance, attention, memory, and self regulation skills. Closed loop learning paradigms. BCIs facilitate closed loop learning paradigms where neural activity is monitored in real time and used to dynamically adjust feedback or stimulation parameters. By continuously adapting to users' neural responses to performance, closed loop BCIs optimize learning and plasticity induction, maximizing the effectiveness of neuro rehabilitation interventions, motor skill acquisition, and cognitive training programs. Brain machine interfaces for motor rehabilitation. BCIs integrated with robotic devices or prosthetic limbs can provide sensory motor feedback and reinforcement during motor rehabilitation exercises by coupling neural signals with motor actions or sensory feedback. BCIs promote sensory motor learning, motor relearning, and neuroplasticity in individuals with motor impairments due to stroke, spinal cord injury, or neurological disorders. Cognitive rehabilitation and memory enhancement. BCIs offer cognitive rehabilitation interventions that target memory, attention, and executive functions impaired by brain injury, neurodegenerative diseases, or cognitive disorders. By engaging individuals in cognitive tasks or memory training exercises while providing real-time feedback on brain activity, BCIs stimulate neural plasticity and promote functional reorganization in brain regions associated with cognitive processing and memory formation. Overall, BCI technology has the potential to leverage neuroplasticity to promote adaptive changes in brain function and facilitate rehabilitation, learning, and cognitive enhancement. By harnessing the brain's intrinsic capacity for plasticity, BCIs offer innovative approaches to address neurological impairments, enhance cognitive abilities, and promote neural recovery and resilience in diverse populations. Continued research and development in this field hold promise for unlocking the full potential of BCI mediated neuroplasticity interventions to improve human health, well-being, and quality of life. Regulatory frameworks, medical device regulations. In many countries, BCIs intended for medical applications such as neurological rehabilitation or assistive communication are subject to regulatory oversight as medical devices. Regulatory agencies such as the US Food and Drug Administration (FDA) in the United States or the European Medicines Agency (EMA) in the European Union classify and regulate BCIs based on their intended use, risk classification, and potential impact on patient safety and health. Clinical trials and approval processes. BCI developers may need to conduct clinical trials to demonstrate the safety, efficacy, and performance of their devices before seeking regulatory approval for commercialization. Regulatory agencies require robust evidence from clinical studies to evaluate the benefits and risks of BCIs, assess their compliance with quality and safety standards, and make informed decisions about market authorization or clearance. Data privacy and security regulations. BCIs involve the collection, processing, and storage of sensitive neural data, raising concerns about data privacy, confidentiality, and security. Regulations such as the General Data Protection Regulation (GDPR) in the European Union or the Health Insurance Portability and Accountability Act (HIPAA) in the United States govern the handling of personal health information and impose requirements for data protection, informed consent and data breach notification. Ethical guidelines and research oversight. Ethical considerations play a crucial role in BCI research and development, particularly regarding informed consent, privacy protection, risk assessment, and potential impacts on human subjects. Institutional review boards, IRBs, research ethics committees, and professional organizations provide guidance and oversight to ensure that BCI studies adhere to ethical principles, respect participants' rights, and mitigate potential risks to research subjects. Standards and certification. Standards organizations such as the International Organization for Standardization (ISO) and the Institute of Electrical and Electronics Engineers (IEEE) develop technical standards and guidelines for BCI technology related to safety, performance, interoperability, and quality assurance. Compliance with recognized standards may be voluntary or required for regulatory approval or certification of BCI devices and systems. Post-market surveillance and reporting. Once BCI devices are commercialized and deployed, manufacturers are typically required to monitor their performance, track adverse events or device malfunctions, and report any safety concerns to regulatory authorities. Post-market surveillance systems enable ongoing monitoring of BCI devices' safety and effectiveness in real-world settings, facilitating timely interventions and risk management measures. By adhering to regulatory requirements, standards, and ethical guidelines, developers, manufacturers, researchers, and healthcare professionals can ensure that BCI technology is developed, deployed, and used responsibly, ethically, and safely, maximizing its benefits while minimizing potential risks to users and society. Continued collaboration between stakeholders, including regulators, industry partners, healthcare providers, and advocacy groups, is essential to adapt regulatory frameworks to the evolving landscape of BCI technology and address emerging challenges and opportunities effectively. Neurosecurity risk. Unauthorized individuals or entities may attempt to access or intercept neural data collected by BCIs, compromising individuals' privacy, confidentiality, and autonomy. Mitigation. Implement strong encryption techniques, access controls, and authentication mechanisms to protect neural data during transmission, storage, and processing. Employ secure communication protocols and encryption algorithms to prevent unauthorized interception or eavesdropping on neural signals. Data breaches and leakage. Risk. BCIs may be susceptible to data breaches or leakage where sensitive neural data is unlawfully accessed, stolen, or disclosed, leading to privacy violations and potential misuse of personal information. Mitigation. Employ robust data protection measures such as data encryption, anonymization techniques, and access controls to safeguard neural data from unauthorized access or disclosure. Implement data breach detection and response protocols to promptly identify and mitigate security incidents. Manipulation of neural signals. Risk. Malicious actors may attempt to manipulate or tamper with neural signals transmitted by BCIs, altering individuals' cognitive states, behaviors, or perceptions with potential implications for safety, security, and ethical integrity. Mitigation. Implement integrity checks, authentication mechanisms, and signal validation techniques to detect and prevent unauthorized manipulation of neural signals. Design BCIs with built-in safeguards and fail-safe mechanisms to ensure the integrity and reliability of neural data and signal processing algorithms. BCI system vulnerability risk. BCI system may contain vulnerabilities in hardware, software, or communication protocols that could be exploited by attackers to compromise systems security, gain unauthorized access, or disrupt device functionality. Mitigation. Conduct thorough security assessments, vulnerability testing, and penetration testing of BCI systems to identify and remediate potential security weaknesses. Implement secure development practices, software updates, and patch management procedures to mitigate security risks and maintain system resilience. User authentication and authorization risk. Weak or inadequate user authentication mechanisms may allow unauthorized users to access or control BCI systems, posing risks to individuals' privacy, safety, and autonomy. Mitigation. Implement strong authentication methods such as biometric authentication, multi-factor authentication, or uses specific encryption keys to verify users' identities and authorize access to BCI systems. Educate users about security best practices and procedures for protecting their BCI devices and neural data from unauthorized access or misuse. By addressing these security risks proactively and adopting robust security measures and best practices, developers, manufacturers, and users of BCI technology can enhance the security, privacy, and integrity of neural data and ensure the responsible and ethical use of BCIs in diverse applications and environments. Continued research collaboration and awareness building efforts in the field of neurosecurity are essential to address emerging threats and vulnerabilities and safeguard the security and privacy of brain data in an increasingly interconnected and digital world. Advanced brain signal decoding. Breakthroughs in machine learning, neural decoding algorithms, and neuroimaging techniques may enable more accurate and reliable decoding of neural signals, enhancing the performance and usability of BCIs for a wide range of applications. This could lead to faster, more intuitive, and more natural interactions between humans and machines, unlocking new possibilities for assistive technologies, neuroprosthetic, and brain-controlled devices. Miniaturization and wearable BCIs. Advances in microelectronics, nanotechnology, and flexible electronics may lead to the development of miniaturized and wearable BCIs that are lightweight, unobtrusive, and seamlessly integrated into everyday life. Wearable BCIs could enable continuous monitoring of brain activity, real-time feedback on cognitive states, and on-demand brain-computer interactions, empowering individuals to enhance their cognitive performance, well-being, and productivity. Closed-loop neurostimulation. Closed-loop BCIs that integrate neural sensing with real-time neurostimulation could revolutionize neuromodulation therapies for neurological disorders, chronic pain, and psychiatric conditions by dynamically adjusting stimulation parameters based on individuals' neural activity and physiological responses. Closed-loop neurostimulation systems may offer personalized and adaptive interventions that optimize therapeutic outcomes and minimize side effects. Brain-to-brain communication. Advances in BCI technology may enable direct brain-to-brain communication, allowing individuals to transmit thoughts, intentions, or emotions to one another without the need for traditional sensory or motor channels. Brain to brain communication could facilitate new forms of collaboration, empathy, and social interaction, transcending linguistic and cultural barriers and fostering deeper connections between individuals. Neuroenhancement and augmented cognition. BCIs designed for cognitive enhancement could augment human cognition, memory, attention, and learning abilities through targeted neurofeedback training, brain stimulation techniques, or adaptive cognitive assistance. Neuroenhancement technologies may empower individuals to optimize their cognitive performance, creativity, and problem solving skills, enhancing human potential and resilience in academic, professional, and creative endeavors. Ethical, legal, and social implications. As BCI technology becomes more pervasive and integrated into everyday life, it raises complex ethical, legal, and social questions about privacy, consent, autonomy, equity, and human identity. Addressing these implications requires interdisciplinary collaboration, stakeholder engagement, and thoughtful deliberation to ensure that BCI development and deployment are guided by ethical principles, respect human rights, and promote the well-being and dignity of individuals and society as a whole. Hello viewers, as we embark on a journey into the captivating world of brain-computer interface (BCI) technology, before we delve deeper, it's important to recognize the multitude of potential benefits this technology offers. BCI holds great promise for individuals with disabilities, providing a means of communication for those who cannot speak or use traditional methods. Moreover, it opens doors for people with congenital conditions, enabling them to contribute meaningfully to society. Essentially, BCI has the potential to unleash the full capabilities of brilliant minds across various sectors, from healthcare to education, ushering in a new era of human-computer interaction. However, alongside its promise, there are concerns that must be considered. We must contemplate the potential negative consequences that could accompany the widespread adoption of BCI technology. Throughout history, humans have held sovereignty over their thoughts and intentions, protected from external manipulation. Yet the emergence of BCI introduces a paradigm shift, raising troubling possibilities. Criminal exploitation. There is a risk that malicious individuals could misuse BCI, violating individuals' autonomy and coercing them into action against their will. Control over prisoners. BCI could grant authorities unprecedented control over incarcerated individuals, leading to ethical and legal dilemmas. Societal discord. Manipulation of thoughts and emotions through BCI could intensify existing tensions, jeopardizing relationships and community harmony. Amplification of prejudices. BCI enabled exploitation of hate, racism, and personal biases could deepen deviance within communities. Manipulation of devices. BCI could allow for the transmission of misleading or harmful commands to connected devices. Commercialization of data. The commodification of neural data raises significant privacy concerns with potential exploitation by profit-driven entities. Data security vulnerabilities. Compromised BCI systems could result in catastrophic breaches of personal information, eroding trust in technology. Exploitation by hackers. Malevolent actors could leverage BCI to exert control over individuals, effectively turning them into involuntary agents. Ethical considerations. Adhering to ethical standards in BCI development and deployment remains crucial, impacting societal norms and values. Unknown consequences. The complexity of BCI technology and human behaviors introduces a myriad of potential scenarios, many of which pose unforeseen challenges. While recognizing the immense potential of BCI, brain to brain or installation of chip, it's our responsibility as citizens to critically assess its implications. In an age rife with data breaches and privacy violations, the integration of BCI demands careful scrutiny and ethical reflection. As we navigate this path of technological advancement, let us remain mindful of both its promises and risks, striving for a future where innovation serves humanity's betterment, guided by integrity and responsibility.